My name is Liz Lathan-Gray. I'm the Executive Director of the Harvard Data Science Initiative. I want to tell you why it's me introducing and not our faculty co-director, Stratos Idrios, because I think you'll appreciate he was going to introduce Pavlos. Both are Greek, but Stratos had to call out because his son, who's 5, built a model of the Acropolis to present in his kindergarten classroom today, and Stratos wanted to be there for it. So I'm sure that Pavlos can forgive him for that. And you are stuck with me. My main job this morning is to tell you that this session is being recorded. There won't be any video of your faces, but if you say anything, that will be picked up by audio, and we will be posting the recording online in the next week or so, so just be aware of that. And now it is my real pleasure to hand over to Pavlos, who is the Scientific Director of the Institute for Applied Computational Science here at SEAS, to lead this tutorial. We are thrilled that he is doing this. He is in high demand for his teaching. I think one of the best teachers at SEAS, and I think that's pretty fair to say. And I'm just delighted that he could be here today to be with all of you. So thank you for being here, and over to Pavlos.
All right. Good morning, everyone. Yes, welcome. I'm Pavlos Protopapas, and thank you, Liz, for the introduction. You put the expectations extremely high now, so they're expecting the best. Let's put the expectations a little bit lower. I'll be your lecturer for today, along with Elaine and Lee. We're going to do the session. How many of you been in yesterday's meeting? I know there were a lot of discussions of the implications of AI, how it's going to change our lives, et cetera, et cetera. In this session, it's a little bit too loud. Just a little bit. Can you hear me in the back? Less, right? So in this session, the goal is not to discuss the importance of AI, which we can do during coffee breaks or afterwards. Not that I don't care, I care a lot. But my goal is to explain some parts, how these things work, and then we can make more informed decisions or informed opinions of what AI can do. Okay, so that my goal is to explain stuff more than discuss it. Okay? So we have 3 hours. I don't know if there's any break in between, but at one point, I'm sure everyone's going to get tired, and we're going to do some classroom yoga, get up, stretch. Otherwise, I'm sure you're all going to get very bored. So the lectures, we have a QR code. They're all there. There's 3 PDFs and 2 notebooks. You must have received an email from me, some kind of homework 0 to get ready. So when we do the tutorials, you don't have to struggle. We're going to do 2 of the sessions with me. Then we have a tutorial with Elaine, and then back with me, and then another tutorial. Okay? So let's start. So first, it's kind of the force. We're going to try to explain a lot of things in a very short time. Please interrupt me if there's something doesn't go through. We can ask any questions. Only thing I have to be careful not to say something silly because it's recorded, and no bad jokes, which I tend to do. But that's my goal. Okay, so let's start. So I'm going to start by explaining a little bit the background and what is word embeddings. Then we're going to talk about attention. Attention is the basic building block for your ChatGPT. We need to understand what it is. And I promise you, when we understand what it is, you're going to ask 2 questions. One is, really? That's it? And then, really? And it works? That's how I feel, and I hope you're going to get to the same conclusion. Okay? So we're going to talk about attention, and then we're going to talk about the basics, and then the building block for transformers, which is the building blocks for BERT and GPT. And then we take the GPT, and then before that, we're going to talk about multi-head attention, position, and coding. These are the 2 basic things, and we bring it all together. In the next session, I'm going to take GPT, and I'm going to move all the way to ChatGPT, if you like. And I'll explain the details. And then the last session, we're going to be talking about RAGs, the retrieval augmentation generation. And in the afternoon session, Mauricio is going to be talking about the cool stuff, which is agent. Okay, so I'm putting the foundation. He's going to do the latest, coolest stuff. Oh, All right. So let's start with, actually, before we get to what is a word embedding, I want to ask the question, what is a language model? The way I like to explain is not on the slide. I like to explain is that if I'm able to predict the next word or a missing word, it means I understand the language, I understand the context, I understand the syntax, I understand the grammar. So if I say, for example, it can be as simple as one hot encoding where it blank. Don't look at the slide. Okay. So, or I say, this morning we all came to the class to listen to. Anyone wants to fill up the blank? Huh? Yes. Any word that makes sense has high probability means you understand what I'm trying to say, you understand the context, and you also understand how English is structured. So now if I do the same one, and I say, Kalimera, το όνομά μου είναι Pavlos, σήμερα θα σας πω. Anyone who's the next one? No one, because you don't speak Greek. That means you don't understand Greek. But if you knew Greek, eventually you will be able to fill up the word. So that's as simple as that. If I'm able to predict hidden words or the next word, it means you understand the language. And that's what we do with these models, okay? So that simple idea, you can carry it on. You can talk about conditional probabilities, joint probabilities, etc. You can throw neural networks at it, and we're going to see later. But the basic idea is, can I predict the missing words? Can we predict the next word? Can we predict the mask word? Okay? All right. Now, the way to do that, and because computers don't understand words, so your neural networks or whatever model you have are usually mathematical operations, multiplications, additions, and some function. Most computers, the way we structure them, would not be able to understand words. They will only understand numbers. Okay, is that clear to everyone? All right, so if we're gonna deal with numbers and we actually have words, we need to translate the words into numbers. Okay? So that's the first step, and we call this an embedding. We take the words and we translate it into numbers. You can take every word in the dictionary and put it. The first word is going to be 1, 2, 3, 4, 5, all the way to whatever the size of the vocabulary. A typical vocabulary size for any language would be anything between my vocabulary about 1,000 and the vocabulary of a native speaker about 100,000. Okay, so about 100,000 is the vocabulary size. Usually we deal with it. Okay, so that's one way of doing it, but that's just not rich enough. It doesn't tell us a lot about the words. Every word now has a number. Another way of doing it is to do what we call one-hot embedding, which means you take a number, binary number, and every bit will be 0 and 1. So for every word, one of the bits will be 1 and the rest will be 0. So you can see it here. The word this will take this bit up, everything else is 0. The word is will get this bit 1 and everything 0. Okay, that's a way of translating words to embeddings, to numbers. Now, instead of giving one number into each word, what I give a vector. It's a vector, it's a set of numbers that I'm going to be used. So that will work, no problem. Computers like vectors. So I put the vector in, and it does some operation, and it predicts the next word. Always my goal is to predict the next word or predict a mask word, a hidden word. So that's one way of doing it. There's a problem with that, or we can do better, I should say, that there is not any semantic meaning in these vectors, in the sense that if I have two words that they mean similar things, I want them to have similar numbers. Okay, if I go back to the example I was saying before, if every word gets a number, maybe the word apple should be 32 and the word or a pear should be 33. Okay, so I want them to be near each other. So we can do that. However, if I want to express multi-relationship, with one number would not be enough. So the word 32, 33, 34, but then you know, there is apple, there's pear, there is grapes, all these fruits. Eventually, I'm going to go far away from one to the other. So another way of doing it is to do these vectors, as I said, because in the vector space, in a multi-dimensional space, I can put a lot of things near each other. But if I do the one-hot encoding, every vector points in a different direction. Okay, so what shall we do? Any ideas? Instead of doing vectors that are orthogonal, we can just do any vector, right? And that's the way we do the word embeddings. Now we have n-dimensional space, and every word now points into this n-dimensional space. But because now I have the flexibility, I can put words that mean the same thing to point in the same direction. So if you think this is a three-dimensional space, fruit will be there, anything about cars will be there, you know, anything about furniture will be here, etc. But because I have the multidimensionality space, I can put a lot of things together. Okay? Yes?
How to decide n?
How do you decide n? And your name? Can I?
Victor.
Victor. How do you decide the name? The n, the number, is kind of user specified. We decide. There's not specific. So, hold on. If I put n very small, I won't have the ability to cluster things, right? If I have n too large, then it becomes computationally expensive and memory expensive. So somewhere between very small and very large is what we use. So 256, 512, that's the typical number. Yep, Victor? Yep. Any other questions before I keep going? All right, so now what I'm trying to do is put the words that have semantically the same meaning close to each other. How do we do that? I'm not going to go. So there's something called word2vec, and I just can give you a very high level. So what you do, you get text, and you see words that they're kind of coming together in the text close to each other, and you say, if they're coming together or they have an anchor word, for example, if I say, if the sentence I have the sentence, Pavlos likes to eat apples after lunch, or in another sentence, Elaine likes to eat oranges after breakfast, you notice that the word apple and orange came close to the word eating. Okay? So by doing this anchoring, you can put all these words together. So you start all the words pointing to some random direction, and then you look at the text and you say, okay, these words seems to be coming close to each other or through an anchor word, and you start moving them until you get them close. Does that make sense a little bit? Yeah. All right, so that's the word2vec. And what we have, for example, man and woman will be close to each other, king and queen will come close to each other, walking and walk will come close to each other, and you get the picture, right? After we do all these operations, what you get people, words to start coming closer and closer to each other, and that's what we call word embedding, or one of the most famous word embeddings is called word2vec, and then there is another one, glove, and that's the way we do it. Okay, this idea I hope is clear. And actually, when the paper word2vec came in 2017, and I read it, I was blown away, because not only it was able to put words together, but you could do algebraic relationship in the sense that if you have king and you subtract the word man and you add the word woman, you get something that it was similar to the queen, which is, at least for me, blew my mind when okay? So word2vec, word embeddings, pretty cool. Okay. So the question is, so now we're going to go from word2vec, which is the basic things, or word embeddings that put words into some vector space and they're close to each other, to the next level up. So the way I see the analogy is that you have naive Bayes, which is a way to do language models without the word2vecs and everything. And then we go into fully connected. This one here means fully connected neural network. Then you go to something called RNN, GRU, LSTM. and then you go to transformers. We're not going to cover that. We're going to go fully from end all the way to transformers because we don't have time. If you want to learn all these things, you can take an amazing course called 109B, which is happening now. All right. So let's go. So one of the things we have, actually, let me go to the next slide and I come back. I'm going to go forward. One of the problems we have is the following. So the way I said, every word gets one vector, okay? But what's the problem with that? Let's see if anybody's picking up. I said every word has one vector representation. Let's take the example apple. The word apple has one vector representation. What does apple mean?
It can have multiple meanings.
Yes. It could be the field, it could be the company. What about the word bank? It's a place you go and do money transaction. It could be next to the river. It could be, actually, I recently read it. If the plane makes a bank to the left, you know what it means. It means turning, I guess, right? So words have more than one meaning. And that's problematic because now if every word has one vector representation, I'm trying to guess the next word, as I was saying before, that would be a problem. So for example, the bank is open on Fridays. Now, if I understand the word as bank as the place with the money or, you know, for money transaction, and then I went to the bank to take a walk by the river, if I only have one representation, I'm trying to predict the next word after this in the second sentence, I'm going to get it wrong because I'm going to think is money, right? So that's a problem, okay? So what shall we do about that?
All depends on the context.
All depends on the context. Thank you. So let's go backwards because so here I'm putting my wish list of what I want in my language model. I want to have context, okay? Now, fully connected neural networks, they have a problem that the context length affects a lot of computation. I want to capture the context dependence. Word2Vec, as I described before, will not do that, okay? Because Word2Vec, it just has one embedding per word. I want to respect sequential nature of the language. Again, fully connected, so I have a problem with that. I'm not getting into the details. And finally, I want it to be able to train this thing in a reasonable time, and therefore I need to train them in parallel. And that will come back to that later. Because one of the problems with RNNs, which I'm not covering here, they can do all these things, but the training is sequential. Meaning in order for me to predict the previous word, the next word, I need to predict the previous word. So it's kind of Markovian. So I have to go one by one. And that takes really long time to train. So my wish list points me to a direction that I need something else besides what we have. And that's what we're going to be doing. This is to explain that. So are we done? I have a lot of memes, just to keep it entertaining. So let's talk about context. Your name?
Ana Maria.
Ana Maria. So let's talk about context. What do we mean by context and how we take care of that? So, by the way, let me introduce you Chester. Chester and I, we're going to have a lot of conversations. Is the character that comes, because sometimes students don't ask me questions. So in order to facilitate discussion, I put Chester. Chester is going to be our friend and even appears in the tutorial. All right, so Chester was standing next to the bank of the river. So I want to understand the context of the word bank. I want to understand the word bank based on the context. What shall I do? Look at the previous words, okay, Ana Maria?
Take the closer words and before and after the.
Okay, so Ana Maria and your name, Ronnie, said either look at the previous word or look nearby words, right? And I agree with Ana Maria, language doesn't always work in one direction. Languages tend to work in both directions. So maybe you want to see that further ahead to understand that word. Cool. So one way of doing it, so the idea here is when I take the word embeddings, these static vectors, and I'm going to change them based on the words around it, okay? Is that clear? So we agree that we need to change these vectors based on the context. So let's look at it. So I start with my sentence. I tokenize it. It means I break down the sentence into words or subwords. That's another discussion. But for now, tokenization, let's simply say it. I take the text and I break it into words. Doesn't exactly work that way, but close enough. Okay, so and then I pass it to word2vec. That is going to give me this static embedding. So what I want is to do some transformation, which I'm going to call contextual transformation, to change my vector. Okay? So I start with the static embeddings, the static vectors, and I say, look, the word bank has to change from the meaning of the word the bank, the money bank, to the river bank. And how do I know? I'm going to see the words around it, and now I'm start moving the vectors around. Okay. So one way of doing it, and I'm going back to Anna Maria's idea, is to look at the words nearby. But language doesn't work that way. Sometimes the word that affects the meaning of what I'm trying to understand could be very at the beginning of the sentence or the end of the sentence. Okay? So the idea of distance relationship doesn't work. Okay? You agree? Yeah. So the true context, the true relationship may not be nearby. Okay, so what shall we do now? We know that we need to change my vectors based on the context, based on the sentence. However, the idea of going nearby is not going to work. So let's go to the next level. We want to change the vectors based on the words in the sentence, but how? Well, I'm going to find some relationship. I'm going to find some coefficients that will tell me how is that word related to every other word. Okay? So that's what I do. I find some coefficients that tell me, I'm not telling you how yet, I'm going to say in a second, but my first step is to realize that I'm going to change my vectors, my static vectors, to something else based on the relationship with the words around, and I'm going to find how to change it based on this coefficient. Okay? So how do we calculate this coefficient? Before I tell you, let's think about it. Any of you here physics or math background? Chris, at least you have to say yes. All right, so one thing we can do very easily is to do a linear combination of the others. Okay? So I want to have these coefficients, and I'm going to linearly combine them with the others. Okay, so let's go step by step. So what we're going to do first, I'm going to say the relationship between my word and every other one, it will be described as the cosine similarity of the vectors. Okay. What is a cosine similarity? The formula is there, but if you're not familiar with that, what it tells me is the angle between the vectors. So two words that they're close to each other, the angle will be is small, and the cosine of a small angle is close to 1. If they're far away, orthogonal, that would be 0. Okay? So basically, think about it. How do we measure the similarity between words? Is looking at the angles between the vectors. Okay? Cool. Clear? All right. So what I do now, I have my static embeddings, which are called U1, U2, U3, U4. And I'm going to try to find the similarity between them by looking at the cosine similarity between the words. Okay? And I call them, this is alpha 1, 1, alpha 1, 2. This is the relationship between every word and every word in this vector space. Okay? So this is my relationship. And then those coefficients, I'm going to use them in order to linearly combine with the other words. So let me explain this. I have 4 words. Let's see, I want the relation of this. I find the relation of this to all of the other ones. And now I'm going to change that by linearly combine with these words with those coefficients. Okay? The coefficient between the word itself is going to always be the highest by definition. So I'm not going to change it a lot. I'm just going to change it a little bit based on the other. So if the word bank starts like that, and I have next to it river, now the word bank is going to move towards geographical location or geological thing, right? All right, so that's what we do. We multiply A and U, and that's my transformation. Now, instead of having static embeddings, meaning every word has one vector, every word now will be changed based on the words in the sentence. I'm going to let this digest for 10, 13 seconds and see if we have any questions before I move on. And I'm going to have a coffee. Any questions so far? So let's recap. We start with static vectors, and we say we're going to change them. The way we're going to change is by looking at the relationship between the words in the sentence, and I'm start adjusting them to be near the ones that are more related. Okay. So one little detail is that actually when you take the cosine similarity, you don't get these coefficients because they don't add to 1. In order to do that, we do something called the softmax. And the softmax makes sure that if you add all these coefficients, you get 1. And every coefficient is higher than 0. It makes them into probabilities. Okay? So that's a detail. Now I have my alphas. And this is the softmax. And now my new vectors, which are called Z, the transform vectors, is a linear combination of the vectors in the sentence, and of course itself. And the coefficients I'm using, how much to combine them, is the relationship between these words. Okay. So the problem we have, so this is good. We're almost there, but not there yet. The problem is that we start with static embeddings, we do some manipulation, we get new embeddings, right? But it doesn't seem to change the way I want it to change. It's not going to change very much based on the context. So what we want to be able to change these vectors in order to give us better language model. Let me explain. So Chester is back, and he has a boo-boo. I don't know why. Chester is back, and he says, can we do even better? And I said, yep, let's add some weights. What I mean by that, I'm going to do the following. If I have a vector, and I want to move it, what's the mathematical operation that moves a vector from here to here? Anyone?
Multiply with some number.
Sorry?
Multiply with some number.
Multiply by some metrics, right? So if I take a vector and I want to move it here, you multiply by a metric, okay? So I'm going to call these weights. These metrics, I'm going to call them weights. And I'm going to take the weights and I'm going to train. Let me explain what I mean. So just a second before we get there, in order for you to, when you read literature, you read the papers, you're going to see these terms query, key, and value. Let me explain where they're coming from. Anybody here with database background? No? Yes. So in database, when we make a question, we don't call it a question, we call it a query. And what we search on, we call it keys, right? So it's the same thing here. So we're going to call query the word that I want to change, keys the word I'm relating to, and value back to them, okay? So now what I want to do, I want to be able to move these vectors before I even get relationships, such as I can predict the next word, such as I can predict the hidden word, okay? So I'm going to take my vectors. I know what I'm doing. I'm doing this relationship. But in order to do better, I'm going to be moving them around. And that's the name of the game. I'm going to take the vectors, start moving them around, such as I can predict the next word better, okay? And that's the thing. So we start with a query. I can start with the key. And I multiply them by a matrix, WK. Okay? So I'm moving them around. I'm moving, and I get what we call the keys. I also get my queries, and I multiply by a matrix. That means transforming the vectors in such a way, and I get my keys, my queries. And now I'm doing my relationship between this and that, the same way I did before, multiply the V, linear combination, and that's it. Now, notice that now I'm introducing these weights. These weights are trainable. Trainable means I am going to adjust them during the training session to give me better language model. Okay? So if you look at the whole thing together, it starts making sense. I start with static embeddings, and now I said in order to change them, I'm going to look at the relationship between the words, and I said, oh, that's good, but I want to do better. So why don't we start moving things around, such as I can predict better later. Okay? And that's the key. Okay? So let's look at the whole thing together. So we have the original embeddings I have, which are here. Actually, let me, how about that? Cool, eh? Technology, AI. Well, it's not AI. I can do this, or I can go back to tradition. Okay, I start with the original ones. I'm transforming them. This is W here. It's just moving vectors around, multiply matrix. I get a new one. I take them again. I transform them. I get a new one set. And then the last one. So now the relationship I'm looking is between these two. So let's do that. Cosine similarity plus softmax. I get the relation which is called attention metrics. And then I get the use, and I linearly combine them, as I said before. And boom, I get my new transform vector. Okay? Now, the formula that I need is there. I'll get to that. I'll be there. So I take the Q and the K, which are these transform vectors. I take the softmax, and I multiply by V. There is some normalization there, which is that normalization there. Don't worry about it. It's just neural networks like numbers between 0 and 1. If you give them bigger numbers, they get a little bit nervous. Nothing wrong. They just get nervous, and it takes them long to converge. So in order to keep everything nice, we just... You had a question. Sorry, I forgot. Okay, so what is the word softmax? It's just a mathematical operation. I have it here. I went very fast, but thank you for asking. It's here. So if I have a bunch of numbers, okay, and I want to make sure they add to 1, and they're always between 0 and 1, there is this mathematical operation called softmax, which I'm showing here. Basically, you take these numbers, you put them to the exponential, and then you divide by the sum of those exponentials. Magically, or not magically, it's easy to see. It makes sure that if you add them all up, and you can see if I add them all up here, the numerator will be the same as the denominator, so it will give you 1. And because it's exponential, it's guaranteed to be 0 and 1. And therefore, we call them probability. And Zhaoli may disagree with me because it's not truly a probability, but they feel like probabilities. Yeah.
That's good enough.
Good enough, thank you. Okay. We have a statistician in the house, so I have to be careful now.
That's why we talk here.
Okay, is that clear? Yeah, okay. All right, so let's go back to our story. I was talking about that normalization. Yeah, that normalization here, this thing, it's just to make the neural networks happy. They like numbers between -1 and 1, small numbers. If you give them big numbers, they just barf on you. They just say, I don't like it. And I can explain why, but for now, let's just keep that, okay? Now, this baby here, we're gonna be, this thing here, it's all that there is we need to know. This is your brick. This is called the self-attention block, okay? The self-attention block is all there is into ChatGPT. I'm making a little bit exaggerated statement on purpose to get your attention, not self-attention, but cross-attention. But this is the building block. Now, if you think about it, it is one matrix multiplication, a softmax, and another matrix multiplication. That's where I look at it, I said, really, that's it? And then I said, how can this thing give us such a good result? Okay? Well, the story continues, and this is the cliffhanger at this point. I want you to get your attention because this is our building block that we're gonna use to actually get to ChatGPT, if you like, or Claude, or whatever, okay? Yes?
Why is this called attention?
Why is called attention? Is that the question? Because what I look, actually there's more to that, but let me first give you the first answer. I look at the relationship between the other words, and he said, which other words should I be paying attention to transform this? Okay? So this paper is called Attention is All You Need because what happened historically, this thing didn't come out of nowhere. People were doing RNNs, and the industry was very focused on machine translation between one language to another. And the way they were doing it is you encode it with one RNN and you decode it with another RNN. But then they realized that that encoding, decoding had a bottleneck. So then they were putting connections between the encoding and decoding, and they call it attention. But it's attention between the encoding and decoder. And then Google came and said, you don't need RNN, attention is all you need. And they call it self-attention. Okay. So I gave you two answers. First one, the second one is more historic. Okay, so this is to simplify. I'm going to put the whole thing here. Now let's make it into a block. If you don't really understand all the details, you get an idea what it is. Now I'm putting it into a nice little block. So I have U1, U2, U3, U4. I put it through this self-attention block, means I'm moving the vectors around, softmax, multiply, and I have, right? So that's the basic thing. Now, you may ask, how do we learn these W's, right? And I said, you learn them. Learning means the following. I'm going to look at the data and see how well I'm doing. Let's say I start with some random weight. If I start with random weights and I try to predict the next word, most likely I will do a very horrible job. If I have a horrible job, that is going to be described through something called the loss function. Loss function tells me how well you're doing, or actually how badly you're doing. And then in machine learning and deep learning, the same, there's a very simple thing. You start with some random things, you see how well you're doing, and then you say, you're doing well? Good. If you're doing badly, bad. Actually, not exactly, because if you just say to my kids or my students, or you're doing well or bad, it doesn't help them. You need to tell them how to change. And that's called backpropagation and gradient descent. I'm going to tell the model which direction to change your weights in order to get better. And that's what we're going to happen now. So we start with some weights, moving the vectors randomly left and right, see how well we're doing. If most likely we won't do very well. And then we tell them, okay, change your weight in that direction, increase them in that direction, decrease them in that direction. Okay? So that's called learning. Okay? So we do gradient descent. The gradients will go down and we'll go to the weights, and we start adjusting the weights now. And we keep doing it, keep doing it, keep doing it until we converge to some reasonable value. Okay? That's called training. Take the data, check how well we're doing. This is called the loss function. Adjust the weights such as now my model gets better. Okay? I oversimplify, but I'm not far from it. All right, so the problem is now all good. Now we figured it out. There is a few more things we need to do before we close this chapter. So the first one, language does not work exactly with one relationship between the words. The multiple, a verb will have relation with the subject. Verb will have relation with the adjective. So there's more relationships that we need to capture, more self-attentions that we need to capture. So we have two problems to solve. The first one, attention leads to limited contextual mapping, and the other one, there's no position information. I'll explain both of them. So the first one is the following. Chester spoke to Pavlos about attention. Okay? There is some relation between the word spoke and Chester. Chester is the one who is speaking to me, right? And there is some relation between spoke and to Pavlos. These are maybe different relationships we need to capture. So maybe one type of relationship is not enough. What shall we do? Multiple. Okay. So instead of doing one attention, let's do multiple attention. Okay? Easy peasy. So attention mechanism number one, attention mechanism number two, attention mechanism number three. So here's my attention block. And now I said, well, I need more of this. Let's put more of it. As simple as that. So now I have multi-head attention. Okay? So this is called multi-head attention. That's actually the built-in brick, not one head. Okay. Is that clear? Just do it multiple times. Now there's a little detail here. If you see now, I have multiple of these transform vectors. Let's see, how many of you doing neural networks on a daily basis? All right, let's see if you're gonna answer. If I have, now I have multiple ones and I want to reduce them back to the original, what shall I do? Concatenate and throw a neural network at it. That's pretty much the pattern with neural networks until LLMs came. You have a problem, throw a neural network as a kitchen sink to that, right? Throw everything in the kitchen sink to a neural network. Nowadays, we have a problem you see later, throw everything in the kitchen sink to an LLM, right? But what we're gonna do is just take that, pass it to concatenate, as you said, and then pass it through a neural network, dense layer we call it, just to give me the right. Okay? That's kind of detailed, but basically what I do now, let's look at the whole story. I have my vectors, multi-head attention. Now I get a bunch of vectors. I concatenate and pass it through a dense layer, and I get that. Okay, so that's now my whole thing. So this is now what we have: multi-head, concatenate that, and I Chester comes said, this is not going to work very well because back propagation is going to get stuck. It's something called vanishing gradient. And now what we're going to do, well, let's just put some skip connections. And now I have the whole transformer. Okay? So these are just tricks we do in order for the training to happen. Yes?
You have to create a new multi-head attention block for every language because they have different relationships.
Yes, the question is, do we have to create a new model, a new model for every language? The answer is yes. You train a different one. Now, nowadays, LLMs are trained on a multi-language, but for now, the simple model, yes, we have one for English, one for Spanish, one for Greek, one for French, etc. Right? And you can train all of them together if you are OpenAI and you have a far more GPUs, but I don't recommend us doing it. So in principle, yes, you can do multi-language, but for this simple model, we do one for each. Yes?
The temperature parameter, which controls the creativity response, is it part of the self-attention block?
The temperature parameter is part of the self-attention block. So there is two kind of professors. One, the answer, I have a slide for that. It's coming. So just to give you a preview, because it's going to take long to come, that only comes when we do GPT and how we predict. Okay, I will explain. Or I go to the board. Any other questions? Okay. All right, that's pretty much it. And now what we can do in order to even make it more complicated and we can capture more things, we stack this together. So each one of these things is what we talk about, but notice this red little block here is a multi-head self-attention. The rest of them is just stacking them up together. As I said, this is your brick. Now you start putting bricks together to make the house. Okay? All right, so I think that's all we have except positional embedding. Positional embedding is the thing that everybody puts under the rug because if you notice everything I said, there's one little problem. So if we take the sentence, Chester spoke to Pavlos about attention. Okay, we understand multi-head attention, blah, 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 stack them up, we get a new embeddings, right? There's a little problem here. What if I change this? Pavlos spoke to Chester about attention. If you look at if you think about all the mathematical operations we've done, nothing will change. All the embeddings will be exactly the same because we take matrices, you multiply them, et cetera, et cetera. There is nothing that will change the embeddings if I do this. Okay? So there's a problem here because there's a big difference between this sentence, Chester spoke to Pavlos about attention, or Pavlos spoke to Chester about that. It's very different. Fundamentally different, right? Who is the student, who is the teacher? Who is, So there's a problem here. So all of these things I said, we still have this major problem that if I change the order of the words, it doesn't change my embedding. What shall we do about that? It's called positional embedding, and I will explain that. Here it is. So if I have the word, because in my input, the word bank will always start with the same vector. So I take it, I transform it, I do matrix multiplications, softmax and everything. If I always start with the same embedding, I'm going to end up with the same attention vector. So one way of doing that is to break that symmetry, meaning that if the word bank appears here or it appears here, it should change the vector before we even do anything. So I want to change the vectors before I do anything, before I do my transformation. So if it's the first word in the sentence or the second or the third or the fourth to be different, that's all I care, just change them. So the way we do it is the following. Okay, let me go on the board on this. That's my morning workout. Look at this box. I have a box full of chalk. So if the problem is that if I have the word, let's say, bank, and it has some vector, if it's first in the sentence, second in the sentence, or third in the sentence, will always be the same. So what I want is, let's say I have the word bank, which is first in the sentence. Here I have the word bank that is third, and then I have the word bank that is, I don't know, 22. Okay? What I want to do is to make sure that before I pass it to my attention, multi-held attention blocks, I want to change them based on the position. So what can I do? Well, maybe you should add a number to it. So I can add the number 1, I can add the number 3, and I can add the number 22. That means now what goes in here is not the same. So I break that symmetry. Okay, now, the problem with just adding numbers is that if I have a sequence length of 5,000, I'm going to have 5,000 numbers, right? And the other important thing is not only if it's the first and the second, I want the relationship between their position. Okay? So this doesn't work very well. I mean, people have tried that, and it doesn't work very well. So instead of just giving a number, I'm going to do a trick, such as the relationship, the relative position matters, but also breaks it. To do that, we're going to use sines and cosines. I'm not getting into the details, but there is a very good reason for that. And this is what at least Google team came about. So they create this new vector that I'm going to add to the vector, which is called PE, position embedding. So I'm going to add a vector which I call PE, which will depend on what position is 1, 3, 22. Okay, so this is a mysterious formula that appears in the paper. This is a position embedding, and the sign and cosine is a very good reason for that because it preserves the relative position, meaning that the word 22 to word 3 will be 19 steps different, and the word 10 and 29 is still 19 different. And this, by doing these sines and cosines, you can do that. And then they have this division by 10,000 to 2i over d model, which is the most confusing thing I've ever seen. And I'm proud to say I understand where is this 10,000 coming from. I leave it for you to come after the thing. I will explain it. So you have something to look for. If you ever bother why this 10,000 is there, I think I have a good explanation because it bothered me for almost 6 months. But I think I know what it is. Okay, so now let's put it all together. So we have Let's look at it at the bottom. Actually, one thing I wanted to say, this position embedding here, you can think about it as, and this is a nice analogy, if I want to encode the position with as few numbers as possible, let me put it this way. If I want to encode the time since the Big Bang theory, Big Bang, no theory, since the Big Bang, in increments of 1 second, how would you do it? You can just write the number. That's going to be cumbersome. Or there's another cool way of encoding time, which is called the clock. Okay? So if you look at the clock, there's 3 hands, and they can encode time in increments of 1 second for 12 hours. And I have only 3 numbers. The big hand, the small hand, and the other one. Okay? Now, you can encode the time since the Big Bang. I calculated that with 12 hands. You can do it, if you have 12 hands in a clock, you can encode every second since the Big Bang to now, uniquely. Okay? So that's why here I'm going to have this clock here, because that's what the position embedding means to me. It's like a clock. And this cosines and sines is like going around the clock. Okay? So, all right. So what is that going to do? Is just going to break this symmetry. I add it here, and then I go through my block, and that's it. I think that's all I have. That's the building block. Let's recap before we go to the next one. I take my embeddings. We understand what embeddings are. We transform them with these matrices. We find the relationship between them, softmax, blah, blah, blah. Then we do it multiple times to get multiple relationships. We stack them up, and then we add position encoding on the top, and that's the basic idea. How am I doing with time? Very late. Any questions before I go to the fun part? Yes?
So a language is alive, right? And we have metaphors. How
Metaphors? Language models don't do very well with synesis and metaphor. They just don't do very well. So especially these kind of models that I'm talking about, they're not going to get it. So there is, the simple answer is they're not going to get it. That's it. The new models now, they start getting a little better by throwing a lot more to it. But this basic language model is not going to do very well, because you're not going to have a lot of examples. And remember, using one thing that you have to understand, we have this is an important aspect. Notice that in all these things, I have no human involved. Everything is just predicting the next word. Okay? And therefore, synesis and metaphors and all these things are not there. Unless you start putting humans in the middle, which explain the metaphor, or explain the humor, or explain that. And that's what I'm about to talk about. We're going to start putting humans in the middle. Okay? But it's a good question to segue to my next thing. The way we learn now is called self-supervised. We never use any annotations. We never ask humans to tell us anything. Nothing. You just text, right? And there is a very funny story. About 2 years ago, we were doing a homework, and we wanted the students to train. So the story is like that. People my age, when we text, we put ... I don't know if anybody my age. My kids think is weird. So I took all my text, which I said something ... and apparently it's not used with the young people. And then the idea was to learn how to predict these ... I write. So the training set we have was from Princeton. It's called the Synesis data set. And the idea was that the students to train through that, because I tend to be a little bit cynical and humorous. And then at 11:55, Chris, which is co-teachers with me, calls me up on the phone and said, no, this is a disaster, because we look at the data, and the synesis could be misunderstood. I mean, it was vile. So we have to stop the homework, clean it up, and do it again. So Language models will not understand the synthesis, will start putting out very, very nasty things. I mean, extremely bad. So to answer you, it won't understand. But let's move to the next chapter, because now we're going to put humans in the middle, who is going to explain this thing. Any other questions before I go? Yes.
How does parallelization come in?
Oh, yes, very good question. How is parallelization come in? I promise I'll explain. I didn't, right? So if you think, because we're learning, we don't have to wait for the previous word. We're learning all of these weights at the same time. So everything goes in, everything comes out, and then we say, let's change all of them. Is that clear? So if you do an RNN, what do you have to wait for the previous word to get to the next one, to get to the next one? All right, let's move now. Let's put humans in the middle, and let's do better. So this is what we have so far. So this is the image from the paper from Google. Attention is all you need. That is started the transformer. As I said, it has two parts because they were doing machine translation. One was the encoding and one was the decoding. So there's two parts to it, the encoding and the decoding. You start with the English sentence, cheeses enhances flavor in any dish. And in Spanish, el queso realza el sabor de cualquier plato. I don't know. Is that correct?
Yes.
Good. I think I think Elaine did this, or someone. We use LLM to do it. Okay, so the idea is you take the thing. First, we do the word-to-vec. Let's explain, because now we have the exact diagram from the paper. We encode it. We do the position encoding. You see here the position encoding. I have a clock. They have a different sign. Multi-head attention, we know what it is. And then we take it and we decode it in the other language. Okay, so let's take first the first part, which is bird. So if you only take the encoder and try to learn the language the way I described it in the first 5 minutes, trying to predict the next word, what we get is bird. Okay? Bird is bidirectional embedding RT, transformer. What is R? I forgot. Huh? Representation, bidirectional embedding representation transformer. Why? Because they wanted to use the word bird, because they like Sesame Street. Okay, if you take only the decoder part, you get GPT, and we're going to get into all these things slowly. All right, so once you have the difference between BERT and GPT is the following. The BERT, or embedding models, will mask some words, mask them, hide them, and try to predict them. GPT, what it's going to do is going to mask all the forward words and try to predict the forward words. Not just mask, everything forward. And therefore, GPT is able to produce text as you go along. So if you start with something and you say continue, it's going to start putting words. The problem, though, and I think we have a GPT, plain GPT in the tutorial. Yes. Elaine is going to show you that if you get GPT and start with some prompt there, it's going to start creating words. The words make sense, but it's total garbage. Okay? Because the only thing you learn is to create the next word, the next word, the next word by predicting from previous. Now we need to go to the point to change that from just producing words that syntactically and grammatically is correct to make sense. In other words, to know the intention that we want them to do that, we need to do something. So what is we call them instruction-tuned LLMs. So what the instruction-tuned LLMs are, large language models fine-tuned to better understand and follow human instruction. Okay. So far, what we have learned is to learn to either predict the missing word or start producing words one after the other. So now we're going to get to the next level. So this kind of tuning will improve the ability to generate useful, relevant, and coherent responses out of that. Okay, so let's go into the thing. So GPT, I said, our models are trained to predict the next word in a sentence given the context of the previous word. It just predicts the next word. It just creates words, and you're going to see an example of that. They don't have access to the specific instructions. of the user, right? And then we don't have human in the loop. So let's go step by step. So the way I see it, this thing here, the first column here is what we call the GPT, and we call it pre-training. And the analogy I got is a wolf. It's in the wild, right? It just generates a bunch of words, right? The first thing we're going to do is called supervised fine-tuning, and you notice the wolf now is becoming like a dog. And then the next thing we're going to do is called the reward model, and then finally the reinforcement level. I'm going to go through all of them just to explain how the whole thing works. So again, the first thing, we get data from the raw internet, and we use the algorithm we do is what I described before, and then we get this wolf. It's wild. It just runs around, gives us words, right? Now let's tame that thing. So this is the GPT we talk about. And actually some numbers here. The GPT here is vocabulary size 50,000. The context length, that's 2,000 words or tokens, 175 billion parameters. And it took 1 month to train on 1,000 to 10,000 GPUs, depending what block you read. And it costs about $10 million to train in year 2020. Okay. I call it penguin killers, because every time we train one of those, we burn so much energy. Okay, that's GPT-3. Now let's go into what we call the fine-tuning, which is a supervised fine-tuning. Now I want to stop there and explain. The way I was describing before, there was no supervision. It was self-supervision. Give you text, hide some words, find them. No supervision, okay? Not supervision from us. Now we're going to do supervision. So the way you do it, you start with a bunch of prompts. Prompts means questions. What is the capital of France? That's a question. That's a prompt. Summarize this document. That's a prompt. Correct my English from this email. That's a prompt, right? So we start with that. So we have a sample of them, and I have a note there. The data is a web-scale corpus of data, including correct, incorrect solutions, math problems, etc. Okay, now I'm going to get contractors, people, humans, and I'm going to ask them to write answers to that. Okay? By the way, DeepSeek kind of found another way of doing that, which is find mathematical proofs and with a verifiable, so you don't need the humans there, but that's another story. So I start with a bunch of prompts. I get contractors to write the answers. Okay? Is that clear? Yep. So now I have now input and output. Now I'm going to change. The word change is important here. We're not retraining. We change the model to give us this right answer. We start with the pre-trained model, the one I described before, and now I'm going to change the model to give me answers that they match with a human. That's a human. Okay? So this is called supervised fine-tuning, SFT. The models, and you're going to see in the tutorial, if you start with the GPT, it gives you garbage. Then we do SFT, which gets better. And then we're going to do more. Okay? Yes?
I've heard online a metaphor of this.
Yeah?
The initial raw training, getting pretty
Yeah. Very good.
Makes sense.
Yeah, yeah. I have somewhere slides. If you have a toddler and want them to answer questions, the first thing you do is teach them the language, which is what I did before. And now I'm teaching them the knowledge, right? I think that's the same metaphor. Yeah. So the first thing is to learn the language, understand the language. Now we teach the model to answer in a specific way. All right. So that's the SFT. Okay. What's the problem with that? The problem is, unless I give many or gazillion of this example, it's going to be good in specific tasks, but it won't generalize very well. So how do we do the next step? So that was stage one, and basically data from the internet, learn the language. Stage two, now we have high quality data with specific tasks, and that takes about $10,000 to $100,000 to train. Okay, so now and you can do that once the first one, you do it every 6 to 12 months. You train the language again because there's new information, new ways of talking. Now we do it every week. You fine-tune the model. Okay? All right, now, at this point, you think, okay, fine. I have my language model. I know the language. I give them a bunch of examples. I learn how to answer specific tasks. What is missing? What is missing is that in order to do this very well, you need to have a lot of examples. And that, therefore, it means that you have to get a lot of contractors to answer questions. And that doesn't generalize very well. And this is where the fun begins. So instead of doing that, and I'm not going to show my slides. I'm going to wave my hands, and then I'll show you the slides. In order to do that, I'm going to pretend the following thing. I'm going to pretend I have a bunch of annotators, contractors, humans. No, I'm going to make a model that is going to imitate the humans. Okay? So the first thing, I got humans to give me question answers. Now what I'm going to do, I'm going to get a model to imitate the humans that was giving me questions and answers. Hold on, I'll explain. So in order to do that, I am going to take my model that I fine-tune, supervised fine-tune, and I'm going to ask them to give me a bunch of answers. That's where your temperature comes in. So I increase the temperature, and now instead of giving me one answer, I give multiple answers. And I didn't give you a good explanation, but I'll go on the board. So remember, at the end of the day, what I'm predicting is, again, a softmax. So I get the softmax, and if you look at the probabilities of the next word, I have a bunch of words. So there is word, 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 word. One way of predicting the word is to get the maximum probability, okay? But another way of doing it is to get all of them and throw a dice with these probabilities, right? So this is going to be most likely, but the others will show up. That's why we have, if you ask ChatGPT, you never get the same answer because it doesn't get the maximum. It gets all these probabilities, just throw a dice, and it gets the one that shows. Now, if I want to get this to be softer, meaning that instead of the maximum to always be very high and everything else, I'm going to soften this, and that means increasing the temperature. If I increase the temperature now, all the words have more equal probability. If I have the temperature very low, the one with the highest probability will be the highest. So even if I draw dice, we'll always get the same answer. Okay, so I was back to this. So now I'm going to get the model to give me multiple answers. Okay? So I give a prompt, and I get multiple responses. Now I'm going to imitate the human. What I'm going to do, I'm going to get humans to get all these answers and rank them. Okay? So here it is. This is the prompt. This is the supervised fine-tuning model, the one I just trained, and it gives me a bunch of answers. Okay? I am going to ask the humans to rank them. So humans said C is better than A, is better than B. So the language model, the SFT model, gives you a bunch of answers. I ask you, and you say, this is better than this, than this. Now I'm going to train a model to imitate that kind of ranking. Okay? So this model here is called the reward model. And the reward model, what its goal is to find scores that for different answers that they follow the human ranking. Okay? So I have now bunch of prompts that they go through the SFT model. I get a bunch of answers. I get the humans to rank them. And now I'm training a model that will give me the same ranking for this prompt. Okay? That's the idea here. So it's to get the model to take in the next step. So now I trained that model. So now I have, actually, this is what I do. There's one little trick here I want to say, that when you train these things to put the same ranking, if you do it, A is better than B is better than C, computers have problems with that. The same thing, I have a problem. If you go to the eye doctor, the ophthalmologist, and he says, okay, there is 10 glasses here. Choose the one that is better. It is a difficult task. So what they usually do, they say this or this. How many of you have been to the ophthalmologist? They just this or this. It's easy to compare pairs than comparing a rank. So I'm going to pair them the same way, and now I'm going to give it to the model to learn this rank. And there is a beautiful thing here, which I maybe skip. But so I have two answers that I got from my SFT. I pass it through the reward model. The reward model gives a score, and I make sure this reward it has the same ranking as the human will have done it, the same pair rank. Okay? So there's this beautiful loss function, which I love so much that I always want to show, but I think we're running out of time. It's my favorite loss function because you make sure the rankings are correct. And I have, actually, you can see them on the slides, on the PDFs, because it explains it very well, or I think it does. So anyway, so there's a loss that you do in order for that model to learn the correct ranking. I really encourage you to go through that loss function. It's just a beauty. All right, so at this point, what we have the model. We pass it through the supervised fine-tuning, so now the wolf is tame. Now I have a reward model that can imitate the ranking that the humans will do, and now we're ready for the reinforcement learning. So reinforcement learning has three components: the policy, the action, and the reward. Now, the reward, we have a model to give us. The policy here is the actual language model, and the action is all the words that you can do. Okay, so here we have the prompt. It goes through the SFT model. It gives us a bunch of answers. Pass it through the reward, and now I'm asking, is the answer I get, will the answer I get rank highly by a human? Would the human would like it? Okay? The reward model tells me that, right? So I got a prompt, I pass it through the SFT gives me an answer, I pass it to the reward, I say, no, that's not an answer that the human would have liked. Okay, so what we do, we have another loss here, and I'll explain in a second, that tells me, okay, you gave me an answer, but this answer that you gave me, the human will not have ranked it high. It wouldn't have liked it. What we do? Go and change the model. Change it such as it gives me an answer that the human would have liked. Okay? All right, so that's what we do here. Then this is the reinforcement learning, and this is a little annoyance here. Some people ask me, but this is not reinforcement learning. You just maximize that reward. It is reinforcement learning. Trust me. There is something there that is reinforcement learning. And again, I give you a very high level. When we do optimization, we only care about the current batch. With this one, we care about the previous batches. And that's why it's reinforcement learning as something. It's called PPO, which stands for Proxima Policy Optimization. At the end of the day, let me just sum it up. What is the goal here is I got a prompt. It went through the SFT, the supervised fine-tuning. I get an answer. The answer goes into the reward model. The reward model says, oh, no, that answer would never be accepted by a human. I go back to the model, change my model, give me a new one. Now the model will say, the reward model will say, okay, that's good. And I keep doing that until I get answers good. There's one final little detail that if you keep doing that, the models collapse into answers that they are very likable by humans. Meaning you will say, it is. The models will collapse into a particular answer. It will say, you're the greatest. Thank you very much for asking a question. This is amazing. And we don't want that, right? So there's something called clipping, like cutting, not the contrastive learning, which it says, okay, change the model, but not too much. Okay? So that's that word clip means there. So you want to change the model such as giving me answers with the high reward, but don't change the model too much. The analogy I have is that if you do that, you always get a poodle, because everybody likes a poodle, but I don't want a poodle, I want the real dog. Right? So you need to make sure you don't end up with a poodle, right? So that's the clipping. And that's all we have. Okay? So let's recap before we get to, I need to give you time to do the thing. Okay. Let's recap. So we started with the from the beginning. We start with understanding what the language model is. Then we did this self-attention business to transform. With that, we generate words. That didn't satisfy us. First thing we did, we put the humans to give us answers to particular questions in order to not only know the language, but to know how to answer the question. That was good, but not good enough. And then we said, okay, in order to optimize this, to do it more, I am going to learn how humans will rank answers and use that in order to inform the model to give us better answers, such as human will give high ranking. That's all. And I hope that makes some sense. That's a clipping that I explained. And this is the whole image now. We start with pre-training. The fonts got a little bit off. PowerPoint sometimes works in mysterious ways. But so you start with the pre-training model, which is the wolf. Then we do the supervised fine-tuning. Then we train a reward model. We use the reward model in order for us to be able to do that. And that's the basis of ChatGPT. Actually, I should be clear about one thing. ChatGPT is not this. ChatGPT is actually nowadays an agent on top of the language model. GPT-4 is this. GPT 4.5, which I just got last night, is this. Claude is an agent. The language model from the Perplexity Sonnet, right? Those are the language models. Those are the instruction or assistant things. What you see on the browser or on your tool is not GPT-4 or GPT 3.5. It is an agent on top of that, which in the afternoon Mauricio will explain. Okay? Just to be clear, if you go to the ChatGPT, you see searching and doing all kind of things. That's an agent on top of this. What I describe now, it is the SFT, reinforcement learning human in the loop, the whole story up to this here. Okay? And if you go through an API and access the language, this is what you get. The language model, not the agent. Okay? All right, so I think that's model training. And here I have a few more slides, but I don't need to go through that. Is kind of information that I think. There's one more slide that because I'm training physics in my background, I wanted to understand scaling, and I found this paper extremely, extremely important, which is the following. If I increase the computing, they call it, meaning either the data size or the number of layers or the embedding size or the number of epochs, if I basically make my model much more and more powerful, will the performance get better? And in this paper by OpenAI, which I really like, they show that actually it does scale. Meaning that if you make the model bigger, if you put more data, or if you do, the model does get better, which is a good result to know. Okay. All right, so I think I'm going to stop here. Just 1 or 2 minutes for questions, and then while Elaine. This one? Okay, you want this, right? Okay. So this is where the thing, so you can set up?
Do the QR code, and it should bring up a Google Colab notebook, and then we'll start.
Okay, questions?
Scaling law was OpenAI and ILIA was one of the.
Yes.
Very recently, ILIA said that we are hitting the data wall, even though the compute wall is not. I was wondering what's your kind of take on that?
The question is, and I kind of agree, is like, as I said before, this is it, right? So I think the increase in the performance we're getting is by ingesting more and more data. After a while, there's no more data to ingest, and then there's the other problem that now the internet and the web is full of text that is generated by LLMs, right? So I think, this is humble opinion, we need some more clever ideas to do these things, right? I found that, just talking about the DeepSeek idea, and actually it's not theirs only. There are 2 new ideas I've seen in the last 2 months I found incredible, is this mixture of experts. and then this verifiable data. So they took all the math books, and instead of doing fine-tuning now with the humans, they just make sure the LLM gives you proofs, right? And they use other kind of verifiable. So you don't need the humans, so they can speed up the thing. There are other new ideas I've seen around, but my opinion is that after a while, we're going to hit a plateau. The agents are pushing the plateau a little bit further. RAGs push the plateau a little bit further. We're going to talk a little bit. But at one point, we're going to hit the plateau. This is my humble opinion, and we're going to need some new innovative algorithmic things, right? Any other questions before we? Yes.
In one of the slides, you showed like at 50,000 vocabulary.
Yeah.
But the tokens were like 300 billion.
Yes. But one is the vocabulary size, 50,000. Actually, GPT-4 is 100,000. But anyway, 50,000 the vocabulary size. Tokens are in the whole data set. How many words you have? How many? Not exactly token and words, not exactly the same. Sometimes we're splitting words into subwords.
Normally, GPT-4, they have multimodal capabilities.
Yeah.
So, can you explain a bit like how does that work?
Yeah, the question is how multimodal works. I'll give a very short answer because we need to make sure we have enough time for it. Go back to the embeddings, right? So the embeddings, we have the words in some vector space. You take the image, you put them in their own embedding space. Okay? So now what I want to do is to put the two embeddings together. Okay? So you take images and captions, and you take the caption and you said, oh, I'm here. I get the image, I'm here. So what I do is just bring them together. It is called clip, but not this clip. It's called contrastive learning image P. I don't seem to remember my acronyms today, sorry. But clipping is subcontrastive learning. That what it does is says, if the caption and the image are associated, a pair, bring them together. If they're not, push them apart. Okay, that's a contrastive idea. So that's the basic idea. Short answer, but yeah. Any other question? If not, Elaine, you need the microphone. I'm back. So let's recap a little bit what we have seen so far. We started from basically scratch, very fast forward. We have seen how to train a language model. We talk how to train a language model. And language model, I repeat, is about the ability to predict the next word or predict words afterwards. And then we built the transformer. Now, from the transformers, we get the GPT was creating a bunch of words afterwards. And we have seen here in the demonstration that's not good enough to create what we call a chatbot. We did the SFT, supervised fine-tuning. It improved a little bit, but not good enough to become an assistant, a chatbot. And then the next step, we went to RLHF, which brings us into the latest kind of models, Llama 3, etc. Now, the next thing we want to do is is to move on, is to make it even better. And the question we have is, these language models are trained or fine-tuned on a particular data set. Okay, so there's scenarios at which the data are ephemeral, they're new, or the data are not out on the web, right? They're not out there. And you want to create a language model that knows about these things. How do we do that? So the multiple approaches we can do, one is fine-tuning the model even further, which we're not going to cover in this workshop, and I don't recommend it so much, except if you want to change the character of the language model. But the thing that is becoming very prevailing is what is called RAG, and which then brings us to what we've been talking about agents, but agents kind of RAG feeling. Okay, so this is what we're going to be doing the next half an hour, talking about that. So Chester comes, he's professor now that we master ChatGPT. Does that make me an expert in LLMs? And I said, oh, we'll have some shortcomings. What are the shortcomings we have and how we improve it? Okay. So, what shortcomings? So as we look prompt engineering, prompting techniques, and you remember a year and a half ago, the prompt engineering was the thing that everybody was taking classes about prompt engineering, how to prompt. You don't hear much about prompt engineering. But now, what happens if you start trying to do something and you have to keep giving examples? So if you go back to by the way, if you don't like cheese, you're going to get tired of me pretty soon. Actually, we have a whole course about cheese. Well, it's not about cheese, but the whole course about making an LLM with cheese. But anyway, so let's say you're trying to get a cheese that you can use for your party. All right, so LLM gives you a bunch of cheeses, and you say, no, I don't like this because I don't like acidic cheese. You give it as an example now, and then you keep going and going and going, and you interact with LLM by giving examples, right? At one point, that will become too large. Okay, so let's look at this example. So for example, below is a list of cheese and their typical aging times. Identify whether the given cheese are aged for more than a year, and then I give a bunch of cheeses. I told you, you're gonna get tired of me if you don't like cheese. I like cheese, just in case you didn't realize. So then I give example. These cheeses are aged more than a year. Cheddar is 18 months, Parmesan is 24 months, and the answer cheddar and Parmesan are more. So what we do, and if you remember about a year and a half ago to 2 years, everybody was doing this prompting, right? So you give examples, 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 in order to make the LLM to give you the answers you want, okay? At one point, what's going to happen is that these prompts that you have, these examples you have to get, is going to be too large. Okay? So the question is, what do we do about that? Even if we have a large memory and we can put a lot of examples, the LLM is going to get the query, the question, and also it's going to get a bunch of examples, maybe 10 pages long, right? Now, it's going to be hard to answer the question. Think about taking an exam, yeah? And I have an open book policy. You come with all my notes for every lecture I gave, and you get the first question. You pass it to the LLM, and then you give every single lecture I gave to the LLM, right? Most likely, it's going to get confused. It's too much information. All right, so what shall we do about that?
Build a RAG model.
Build a RAG model. Thank you. That's pretty smart. Well, let's forget the RAG. What would you do if that's, let's say you take an exam. Most of you haven't taken an exam for a while, but nevertheless, you're taking an exam. It's an open book. You have every lecture I gave in PDFs. You get the first question. What would you do first?
Query based on the question.
Look, query based on the question. What is the RAG stands for? Retrieval. So the first thing I'm going to do, I'm going to go back to all my data, all my PDFs I have, and find the relevant information. That's RAG. Okay? That's it. So let's do it. So production to RAG, naive RAG. So I'm not getting into fancy RAGs, but I think half an hour is enough to. So training data is not frequently updated. That's the first thing. So if you go and take an exam, again, the exam question is going to continue. If you're going to take an exam and you don't have your books with you or the PDFs, you won't be able to answer because I have particular things I teach in particular way, particular questions I want you to know. So we don't have the knowledge. The LLM will not have the knowledge that I want you to answer the question. So I'm going to take all the books. That's going to be the knowledge base. And I'm going to keep them there. And before I answer every question, I'm going to find in my knowledge base the relevant information, give it to the LLM, and say, answer. Okay? So let's do that. So this is the retrieval. You retrieve. You augment your question to generate the answer. Okay? That's what it is. Okay. It's quite straightforward. So if you have many documents, how can we process query them using an LLM? Now we're going to get to understand how we do that. Again, back to my example with the exam. You have all the PDFs or all the documents or every class I gave. It's a lot of them, right? So one way is to give everything to LLM. You give it to the LLM and it jiggles and it gives you garbage. Okay? Shall I repeat this? It took me half an hour to make that. You should get 2 seconds of glory. All right. So the content is too large, and the LLMs gives out garbage. The reason is too much information. You won't know what you're referring to. So this another way we can do is to fine-tune our LLM using the data. Okay, so now we do that. We can do that, but it takes too long to train, and it's too expensive. I'm warning you, don't try to fine-tune your language model for everything you do, because it is expensive. In the class last semester, students didn't listen to me, and they end up with a bill of $3,000 from Google, and then we have to go back and ask them whatever. So that's the second one. Let's talk about RAGs. So the RAGs will solve all our problems. All right. So here is a deep look on RAGs, and usually this is the thing you'll find. And when I see diagrams like that, my head spins. Okay, let's just break it down into smaller things we understand. What is a RAG? It stands for, it's a technique that improves the performance of LLMs, especially the tasks that requires accurate and detailed information. So a simple breakdown, we have a user. This is the key slide. It asks a question, it goes to the RAG, it goes into a vector database, okay? And I'll explain everything, don't worry. And then we take the relevant information from my knowledge, give it back to that, put it into with the question together with the relevant information, back to the LLM, and then I get the answer, okay? All right, let's open this up. So let's say I have a document about cheese. Okay? So I have a document about cheese, and now I'm going to have what are different techniques of cheese making. So I have my documents about cheese that I found, and I have it into my knowledge base. So here's my query. So I found the relevant part of my document that talks about cheese making, right? The rest of the documents talk about flavors of cheese, where they're made, what to pair them with, which wine goes with what condiments to go with. But there is a part of the document that actually talks about making cheese. That's the one I want to give to the LLM with my prompt. And then he said, okay, you know a bunch of things, but here is some other information I know about it, and go and do it. Okay? So now I put it together, and we call it the context. You ready for that? Then you have the different technique of cheese making art. Okay, so that's the idea. All right, now we're going to talk about naive RAGs, and warning: naive RAGs by themselves don't work very well. We need to go into advanced RAGs, and I don't think I'm going to have time for that, but I'll give you the slides and the videos if you want, how to improve RAGs. But let's get the basic idea of RAGs first, and then we go to the next. So I know knowledge base. Knowledge base is all the documents I have. In my case, it's going to be about cheese, right? I did download every single book that is written about cheese from Gutenberg Think and other sources. I actually bought some books, PDFs, and I created a huge knowledge base about every single book about cheese I could find. Okay? So the first thing we're going to do, we're going to chunk it. Okay, so we're going to take the documents and make them into smaller parts because the knowledge base is too large, right? So now we're going to take every one of these chunks, and you remember what we did in the beginning today. We talk about these vectors. Okay? So I take the words and I represent it as a vector. I can do the same, exactly the same. I take a chunk of text and I represent it as a vector. What is that part we did? We talked earlier today about the transformers, the blah, 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 the self-attention thing. That's what I'm going to do. For every chunk of my documents, it's going to become one vector. Okay, is that clear? Same way I was describing before. Every word became a vector. Every chunk now becomes a vector. How? It's very simple. You take all the words, you get the vectors, you average them, and that's the vector of the paragraph or of the chunk. Okay, so far so good? Yep.
How do you decide how much is?
How do you decide what's the chunk size, right? Is that what you wanted to ask? I have slides for that. The naive RAG, you decide on the number of characters, but you can already see that's a problem because you're going to cut sentences into the half. you may not get enough together. So there's something called semantic RAG, which you find the chunk that talk about the same thing, the text that talks, and you make it into one chunk. Okay. Any other questions? Okay. So now, all these embeddings, all these vectors, they're going to go into a database. This database is special for vectors. Like any database you have, database just tables, right? And it has, for example, name, age, occupation, blah, blah, blah. You have rows. Now, in this database, it's specialized to have vectors. Okay? So just a bunch of vectors. Okay. Now you start with the query. You ask the question. That query will also be embedded. It means it's also going to become a vector. Okay? And now I have my query is a vector, and I have a bunch of vectors that represent every chunk. And I have to find out which chunk is closer to my query. How do we do that? Cosine similarity. Thank you. So after I do the cosine similarity, I'll find the vector that is closer to my vector of my query. Now I go and take the text associated with that vector. I put it into my context, and I pass it on to the LLM. Easy peasy, right? That's what RAGs are all about. The rest are detailed, but this is the main idea. Okay? Any question? I'm sure you have questions. One is what's the chunk size? The other, for example, how does this database will work? The other one is, will actually cosine similarity give me good answers? There's all these kind of things we can talk. But let's continue a little bit more. So I get that, and I do that. Now, another example I want to besides choose is that if you have an organization and you have, let's say, patient data. Patient data would not be in the LLM. LLM would know nothing about your patient, but your patient data could be your knowledge base. So if I want to ask a question about particular patient, Mr. Smith, for example, and I ask the LLM, your ChatGPT, about the diagnosis of Mr. Smith, he won't know. But now I can go into my knowledge base, find the relevant information, put it into the query, pass it to the, not a good idea to pass the patient information to the API, but nevertheless, that's another story. But you get the idea, you get the gist, right? So the knowledge base will allow us to do this kind of things. All right, so what is a knowledge base? Let's think. It could be websites, it could be PDF files, it could be Word files, it could be anything you want, as long as we can take them, chunk them, and make them into vectors. All right, so here is the whole thing. Now let's talk about chunking. So chunking refers to the process of breaking down, segmenting information to smaller, more manageable pieces. So this is what we do. We chunk them into pieces, and Ronnie? Is that the name, Ronnie?
Ajay.
Ajay. Ajay asked, how do you do that? There is a whole, this is the naive. We chunk them based on the number of characters, but we can do it smarter by looking at finding subtext that is relevant. And how do we do that? Cosine similarity, of course, but that's another story. Okay, so we got that. There are different methods of chunking, which we'll discuss in the upcoming lectures. Actually, this is from another workshop that I have more time. I'll put the PDFs. All right, so this is the chunking. Let's say the embedding model. We talk about that. What is an embedding model? We take that and we pass it through some kind of embedder, which is what we talked earlier today. The BERT is an embedding model. OpenAI has its own embedding model. Perplexity has its own embedding model. Llama has its own. Everybody has their own embedding models. They're all based on the same thing I talked earlier. It is self-attention layers. Okay, that's what they are. Okay, they just go through that, and then you get these Z's I have. That's the embeddings. Okay. All right. So we have the embeddings. We use an architecture similar to BERT and aggregate the words embedding. So you get word embeddings, and then you aggregate. How? You take the average. You can do all kind of things. All right, so what is this indexing? So semantic embeddings, we talk about that. So I wanted to go back a little bit to that. What does it mean to find two sentences that are similar, or a sentence and a text chunk that is similar? We talk about cosine similarity, but, okay, so we're here. So let's talk now about vector database. What is a vector database? Anybody here, I asked before, anybody has familiarity with database? Only one person threw the hand up, but the idea here is that, so basically most of the data in the internet will be unstructured. So if we create vectors, we need to create these databases, and that's what we do. Now the question is maybe a little bit technical, but I wanted to address it. Why do I need a vector database? Imagine I have a knowledge base, I chunk it, and I make a bunch of vectors. Okay? Now, when I come and ask which one of these chunks is similar to my query, what would you do? We said cosine similarity. Okay. Now, that means to find the nearest one, I have to go and check for every one of them. Now, that works nicely if you have a small document, you have 20, 30 chunks. But imagine now you have a knowledge base that is large, and you have millions of chunks. Now, for every query, I have to find the relevant one. It means I go and compare to each one of them, and therefore that will be very slow. So what do we do? Indexing. Okay. What is indexing is, give an analogy for databases. If I want, for example, we have a database for all of us and our age, and I want to find which one is closer to my age. I'm very glad that I have people at my age in this class. Usually I'm the oldest. So what do? We don't check every single one of the person in the room. What do? We sort them. And they say, go halfway. If the halfway is younger than me, I go to the bottom half. I go halfway. This is a very simple analogy, but pretty much covers what we do with indexing. Then I go to the bottom half, go halfway if he's still younger than me, and I keep going. So that makes it much faster. This is the same thing here. In the vector database, they use indexing in the same way we have I described. It's called hashing or local hashing or everything. I think I have 3 ways we do here. Where is it? Here's my indexing. There's multiple ways of doing this hashing, this indexing. One is called local hashing, which I think is not relevant to our discussion. Yes, locally sensitive hashing, which is, I think is called the $1 trillion algorithm, because that's what Google started with. When Google started the search engine, they started with this local hashing algorithm. Not exactly this, but that's what made Google the search engine. There is something called quantization, and then the most one that I've seen these days is this HNSW, hierarchical navigatable small word. It is a way of actually searching in a large database with a lot of vectors, which vector is the closest. Okay? So this is what indexing does, and that's what vector databases become very popular. If you're interested, what vector database should we use? We all start with ChromaDB because it's the cheapest and freer. Then there is FIS, there is Pinecone. I forgot the rest. Which one we use? We know which one we use in the ChromaDB because it's free. So there are multiple databases that they do that. There is some advantage of using a vector database is because now if you have new data and you want to put them in, you want that to be fast. You don't want to re-index from the beginning. It gives you all these advantages. Okay. So, so if I do what are the different techniques of cheese making, it's going to be the query. It's going to go there and it's going to compare. I have some slides which maybe some of you very familiar, but we talked about cosine similarity before as the angle between two vectors. I have a little bit more naive way of explaining this, which is the following. Remember, I'm not comparing words, I'm comparing the vector representation of the words. So let's play this game. If I'm trying to find out who is more similar to myself, to Pavlos, among the TFs, among the teaching assistant, my graduate students, the way to do it is not just get the photo of me you want to get a vector representation of me. So when we ask what's most similar to Pavlos, usually we talk about character, right? So I have Ignacio, I have Harkun, and I have Varshini here, 3 of the people in the lab. So we get the big 5 personality test, and we did this for fun. So what we say now, I'm going to represent Pavlos with a vector of 5 numbers. And those 5 numbers is the big 5: extroversion, emotional stability, agreeableness, conscientiousness, and imagination. I made those numbers, so I look cool. Actually, no, we took the test. Okay? So we get a bunch of numbers. Now you represent me with a vector of 5 numbers, and you represent Ignacio with 5 numbers, Harkun and Varshin with 5 numbers. Now, if I want to know who is closest to me, I'm going to take the cosine similarity of those vectors, and that's what we did. And then we found that Ignacio is the closest to me. Okay, but that idea carries on with this. If I want to know which of the chunks look more similar to my query, is equivalent of getting this vector representation of the chunks and a vector representation of the query and compare them in this vector way. Okay, so now how we compare, we kept saying cosine similarity, but cosine similarity is not the only way to measure similarity. Cosine similarity is one. Cosine similarity has some cousins. Euclidean distance is a distant cousin to cosine similarity, and what we call the dot product is the closest cousin to that. Okay. Each one of them are not very different from each other, but they're better for different things. So I have a slide, I believe. Oh, sorry. That I apologize. Okay. So cosine similarity, I have the definition of what is measured, the cosine of the angle between. I gave you the range. The strength is focused on direction, ignores magnitude. When to use text embedding. Okay. Then you have things like Euclidean distance, used when they're working with numerical feature vectors, metadata, and tabular data. And then the dot product is the ranking document based on relevant score. We use, yes, Charlie?
Just to, cosine similarity is just linear correlation.
Yes. It's the dot product, but with normalized. Yeah. Yep. A linear correlation.
Linear.
Yeah. Yeah, you can do non-linear correlations, but those are expensive, so we use this. Okay. All right. Now, a couple of things before we get to the last part. We did the query. We use that. We find the cosine similarity or any similarity score. And I'm going to get, okay, so here at this point, I find the nearest neighbor, or doesn't have to be the nearest neighbor. We can do the k nearest neighbor. Okay? So at this point, we can just, instead of getting only one, we can get k. We rank them basically, and we get the top k. What is k? User specified. Usually what you do, you keep adding until your context is full. Your memory can do it, and you just yeah. Yes.
Just a question. When you build a conversational RAG, there is first user query, and then some response comes back, and then now you have a second query from the same user. How do you perform the embedding and searching the database? So do you just search for the second query? Do you put the first query, response, second query all in the context? How does that work?
Okay, so it depends on the implementation. Let me repeat the question. If you have conversational RAG, how do you do that? There's multiple implementations. There's not one as far as I know. Actually, I know there's not one. The simplest thing you do, you parse your first query, you go to the RAG, you get the response. And the second time, you just take the second query, find the relevant RAG as before. And now when I go to LLM, I get everything from the history, plus this query, plus a new chunk, and I keep going. So that's implementation I know. Any other questions before we wrap up? All right, so as I said earlier on, this simple RAG works up to a point. You will find that couple of things. One is the chunking. We talk about it. It won't work very well. The other thing that is, and it's not in the slides, but I can tell you one thing that is very popular these days. You take the query, and before you pass it to the LLM, you pass it to an LLM to give you a better query. Okay? Sort of what you need to do with me. You take what I say and you pass it through LLM to correct. So it has become very popular. You do, because sometimes the queries are messy, right? So they take the query, you pass it to LLM, said structure it, you get it back, and then you pass it to them. That's one thing. The other thing that we do is the chunking we talk. The other thing we do when we do take the results from near SK with the vector, we do another pass to find the relevant information. Because cosine similarity is notoriously not good when you have a very high dimensional space. Everything starts looking the same. So you do the cosine similarity first to get, I don't know, the first 100, and then you do another re-ranking, which is another story, to get the ones that are relevant. Okay? So that makes it even better, and then you can do graph racks and all kind of racks, but here. One thing that we usually do is called metadata filtering. I'll give you a good example. So we are working, in a particular project I'm working, we're trying to find relevant citations for a paper. So I have a sentence, and I ask this sentence, what citation should I put? So it goes now to the rack, which is all the other journals, and it comes with a certain number of citations. Except one thing. Sometimes in my database, I have papers that they're ahead of where I am now. Okay? So I want to put a filtering. I would say, yeah, don't use any citation after that date. Okay? So how do we do that? You don't want to do it in the rack. You do what is called metadata filtering. You can, for example, you again back to the citations. I just only want authors or only want from peer-reviewed journals, right? I don't want to use the archive. But in my database, I have things on the archive. So this is what is called metadata filtering, that to constrain down the number of the relevant chunk. So that's called metadata filtering, which is an optional step, but we do that very often. And then you have kind of fancy word to say how do you combine them. Instead of saying combine, they call it rank fusion. All right, so that's metadata help. So for example, author, publication date, and category, right? So category will be, give me only relevant papers that they are peer-reviewed journals, not everything else, or only give me through the archives. And that's pretty much it. So now what we do, we get the relevant information, we put it together, and so this is a slide just to clarify some of the language, because I get confused, and I'm sure you get confused. What is a prompt? What is a query? So prompt is something you give to the LLM from the beginning. It's called system prompt. It said, you're going to be an expert in cheese. You saw that before. And I think Elaine showed one slide with this. Query is the query, and the context, everything you get out of the vector database. And then you put it together happily, and then it goes to the LLM. So in this case, explain the key techniques and concept. What are the main steps, methods used in cheese making? And this is the context I found. It goes to the LLM, and now it's going to go to the LLM, and I get back my answer, right? Well, already talked about LLM's previous session. Nothing new to add here. And this is what we started from. What is a vector database? We know. What is a query? I hope you know. What is a context? We know. What is embedding? We know. And I'm done. That's all for racks. I'm saying, I hope you get this idea. This is a build-up. I make these slides 2 months ago, and by the time I came here, DeepSeek came around, and I asked, actually, Liz, shall I talk about DeepSeek? And she said, well, you can talk on the side, because we said to do something, right? It is, in some ways, a fun field. It's moving very fast. It's fun, but at the same time overwhelming in two ways. For me, it's overwhelming because almost every day someone is going to send me a text saying, have you seen this? I'm like, stop sending me, have you seen this? But in order to alleviate this problem, every 2 months, I sit down and I see every model there is, and I make a summary. If you're interested, I can give you, I call it my fluff talk because it doesn't talk about concept. It's telling you what's going on in the field. And the second thing that is overwhelming as an instructor, every 3 months I need to change my slides because this is moving too fast. My slides from last year are totally irrelevant for this. We have slides on prompt engineering. Nobody cares about prompt engineering anymore. Here goes 10 hours of work, right? Well, I guess it's part of the job, right? But it's a fun field. I did not talk about the implications of AI. We have a session yesterday that I think more experts better than me, they address that. I just wanted to talk about some elements, how this evolves. RAG keep evolving, and then on top of that, you get agents. And I'm just going to give 2 words about agents. Imagine now you have a query that is not in your knowledge base. What would you do? You go to the web. Now, for LLM to go to the web, it has to know that it has to go to the web, and it has to know how to do it. So agents that you're going to learn in the afternoon, it's basically that extra step. Think what I need and execute with tools. Okay, so that's the natural evolution after that. Okay, thank you. So we're going to have Lee, who's going to demonstrate RAGs for you. So at least you see I'm not lying. It actually works the same way Elaine showed you before, and you ask you why you're doing that, just to see I'm not lying. I'm not making things up. You can see them in action, right? SFT improve, RLHF improve, and as you go improve. So Lee is going to do it. Most likely it's going to be about cheese again. So while he's setting up for this class with teaching, we're doing all cheese, and then eventually we make a website, which is called formaggio.me. It's actually live. You can use it and anything about cheese you want. All right.
Very interesting using multiple embedding models. Multiple embeddings?
Thank you. Mixture of experts. So the question is, how about if I have I'll take a second. The question is, if I have multiple embedding models, can I use them and then combine? Is that the question? I haven't seen that, but there is a lot of interest now, mixture of experts. Basically, you get a bunch of answers, and then you decide how to combine them. That would be an interest if you have that. Yes.
What is LLM adding in here? I mean, are we assuming that that knowledge is already in the LLM?
Yeah, very good question. Let me answer. I think we have it in the tutorial. So the question is, you have the knowledge base. Why do you need the language? And I think the way I ask you, you can see the answer, right? The language model is the one who's going to construct the answer, right? Yeah. The language model, you need the language. You need a language model in order to get an answer that's coherent and everything. But a good question I usually get, what if the language already knows the answer? Which one is winning? And that's called self-RAG. The self-RAG asks first the question, do I need this answer? Go back to my example of an exam. You get the first question, do you go to your notes or you see if you can answer it? You first just, that's called self-RAG. And that's where they're using LLMs as a judge, as a critique before you do anything. But I think in the example here, Lee, do you have there is one prompt we said, only use the knowledge base. You can put it into the prompt. Said, don't use your knowledge, only use the knowledge base. And the LLM only is used to create coherent answers, right? Or you can say, use the LLM first and only use the chunk I gave you if you don't know. So you can play these games. Yeah. Good question. Okay. Lee.
Hello, everyone. My name is Lee. I was a data science master student here at Harvard, and I'm helping with various courses, Pavlos. So I'm going to quickly go over the RAG tutorial. We actually have 3 of them. The first one is about building the naive rack from scratch. Where time, I'll just focus on this one. The second is to use the ChromaDB vector database, and the last one is Llama index. So the ChromaDB and Llama index there, you can, in the slides, there are 2 more QR codes that you can scan them and take a look. Feel free to do that. So I'm going to jump into the from scratch, building the naive rack from scratch. The same way, setting up the OpenAI API key.
Nick, can you make the font bigger?
Yep. The same way, put it here. And now, let's jump into the building the naive rack. So let's look at our knowledge base first. I'm going to reading our cheese knowledge base, which is 11 books about cheese. Okay, some imports. Reading the keys. And here are the books. So we have the data set have 2 columns. One is the title of the book. The second column is the context of the book. Context. Hello? Okay, how about this? The second column is the context of the books. Just take a look of the first book, the Project Gutenberg ebook of There's a Pinning and Cheese to Come. Okay. The first book contained around 200K characters. So for doing the rack, we have the knowledge base. Now we need to build up the vector database. Remember what Pavlos just said? We first do the chunking, the indexing, then build up the vector database. So here is what we're going to do. First is tokenization. So there's the audience asking about the OpenAI, I think it's called byte pair encoding. So this is the byte pair encoding, this CL100K base. We load them. We can take a look of how it works. So this is a sentence for demo. I've never heard from LLMs before. If you use the OpenAI byte pair encoding, so this is the tokens you got. So we have a period as a token. We have I and F as 2 tokens. So if you just use the word tokenization, the IVE will become 1 token. So here, OpenAI actually make it 2 tokens, which is very nice. There are other ways to tokenize it, such as like word tokenization. Each word is a token. It can be character tokenization, so each character is a token. You can do sentence tokenization, each sentence as a unit, and so on and so forth. So you can build your tokenization and corresponding vocabulary. So here we use the OpenAI tokenization. Let's look at the distributions of the sentence lengths. So we have 11 books. There are 3 books have tokens more than 100,000 long books about cheese. Go back a little bit.
Well, a little more. When you look at the decoded text, the LLM is no longer LLM. It becomes 2 numbers, LL and
That is right, right?
Is it an issue? The LLM is 1 concept.
So the question was, the LLMs here become 2 tokens, right? LL and M's. So let's try make M capitalize. And what's the result? Okay, so here is L and LM, right? Large is a token. Language model is a token. Okay. It is what it is, right? Okay, so next, what we do is chunking. The first step is chunking. There's an audience asking about the chunk size. We made a helper function to do the chunking. So logic is, we first split the text, the books into sentences, and we fill into the chunks. And then, if you have a long sentence, you kind of have to, chop it and put it into different chunks. There was a question.
Is the chunking and tokenization stochastic or deterministic?
It is deterministic. This is a naive way of chunking. So I think Llama Index API provide like a better way of do the chunking. You can specify the chunk size. Here the default we set is 200. So each chunk has only 200 tokens. I think Llama Index default is 1024. There's idea of the context continuity. So here we want maintain some overlap between chopped chunk to maintain some continuity of the text. We just do a very simple chunking here. So ideally, the number of tokens divided by the chunk size should equal to the number of the chunks using this approach. Let's look at the chunk length in tokens. So this is the number of tokens in each chunk. So you can see most of the chunks have around 200 tokens as expected. Did I run this? Okay, then we save the chunks. Next step is embeddings. So once we chunk the knowledge base, we use some embedding models. Here we use OpenAI embedding models, the text embedding 3 small, to make the chunks into the vector. Chunk embedding or sentence embedding. But to do this embedding, it takes around 30 minutes and costs you money, right? So we did this for you, and you can load it here. So here, each row is a chunk. We have a new column, which is number of tokens in this chunk. We have another column, which is the vector, the embedding of this particular chunk. We have in total 3,352 chunks or embeddings in our vector database. There's no indexing happening here. So we don't use that $1 million algorithm here to do the searching. If you use ChromaDB or other vector database, they're gonna use the optimized way of making it like a vector database. Once we build a vector database, we do the query. The user send a question, and this question, we have embedding for this question, and use this query to retrieve the most relevant information in the vector database. So here, my query is, what is a Gouda cheese? Which is a very simple query, right? A pre-trained LLM probably can answer this well. We define the cosine distance, which is 1 minus the cosine similarity. So Pavlos said cosine similarity is, to compare 2 vectors, and it's below, and the range is -1 to 1. So 1 minus the cosine similarity, that's 0 to 2. So we want to maximize the cosine similarity. Here we minimize our self-defined cosine distance. And we calculate this cosine distance between my query and the embeddings in my vector database, and retrieve the top 5, the most relevant embeddings in my vector database. Any questions so far?
knowledge base that we have, right?
Hmm?
The information is coming from the books that we have.
Yes.
Why do you choose to do cosine distance?
You can use cosine similarity. You can use other metrics to choose.
But why do you want to just do one line?
Well, I don't have to. The people who wrote this code do this way. So use cosine similarity. I want to find the one close to 1, right? Here, 1, 1, find close to 0. We minimize the metric here. Yeah. There's another question.
What's like a normal number of chunks you would choose to not be too much context, but enough? Like you return 5 here, but
yeah, it's on you. You can choose 20. It depending on how many relevant information you want to fit into the LLM, right?
But at a certain point, it's getting to be too much, right? Which is the original.
Yeah, yeah. So there's clear trade-off, right? So you want to choose limited but most relevant, or you want to like gather more context information.
I would say it depends on your knowledge base. If your knowledge base has a very diverse knowledge, I will go with smaller chunks, just to make sure that if your knowledge base has homogeneous data, I'll make bigger chunks. But those are rule of thumb.
Let's take a look of the retrieved information. Okay, the most relevant one, right? The first one. In shape, the Gouda cheese is somewhat like a cheddar with the sharp edges rounded off and sloping towards the outer conference as middle from the end faces. Okay. It was talking about Gouda cheese, right? And if you look, all these 5 retrieved information, they are all about Gouda cheese. Now we have the retrieved context from the knowledge base. We have the query. These two will feed into a LLM. We made a template. So here, we put the query here. We put the relevant information here. And we give it 2 shots, 2 examples, like how to answer the user's questions. Here is the final. Oh, actually, I have a further question here. So I asked it to answer if none of the extracts are related to the query, respond with I was unable to provide any relevant information, so that I know that my retrieved information is not useful here. So here is the final result. We used the LLM GPT-4o. Final answer, Gouda cheese is a popular semi-hard cheese that originates from the Netherlands, specifically southern Poland. Was the information available from the extract? Yes. So this is like a very simple example, right? But for depending on the use case, it can be patient's data, legal data, right? Some data that LLM are not good at, and you can use that depending on your particular use case. And as LLM getting better and better, you will get better and better system. So this is the naive RAG from scratch. The second tutorial we have here is VectorDB. Exactly the same thing, except that we do not build the vector database ourselves. This is 2.2. So here, what we're doing is we use the vector database to build. We use ChromaDB to build the vector database, and there are many types of vector database such as Pinecone, Vice, and I believe there is a link here that you can take a look at the ChromaDB API. It's somewhere in this notebook. But it looks like this. It looks like this. You specify a path, you define client, and this collection is to do the indexing. So this collection is to do the indexing. And you use add methods to adding your new documents into the ChromaDB vector database. That's all I want to share. There is another tutorial about the llama index. There are like a better way to do the chunking for the text. I think in general it looks like this. So there is llama index provide a document object for your text data, and you can use this sentence splitter API to do the chunking. So here I chunk the text. The chunk size is 2024. I have a chunk overlap, which is 20 to maintain the context continuity. This is the people doing to do the chunking. That's all. Thank you very much.
Are you done?
Yep.
All right. All right. Thank you very much. It's 12 o'clock exactly, so limited time. We couldn't get into all the details, but thank you for coming. I'll stick around if there are more questions for the next half an hour. Thank you.